Bueno, buenas tardes a todos.
Good evening, and I hope that you can hear me because I know that I speak quite low, and I hope you can hear me with this microphone I'm using in spite of the time. I know you're all tired, but let's try and tell you about the role that mathematics plays in cryptography, and to tell you that they're essential, that they've played an essential role, a very important role, and that they can keep on playing a role, much more so than up till now. Also try and see some of the lines that seem to be more promising and where mathematics can help in cryptography. And I'm sure that we're all convinced of the fact that cryptography is an essential pillar of cybersecurity because it plays a very important role in security. And it's not just based in cryptography, but it couldn't exist without it. And in cryptography, mathematics have played a role that has surprised even mathematicians. I have here a sentence, a quote by Codebased, where it speaks about how useful mathematics are in physics and in nature science. And I hope you'll agree. It says that a huge usefulness of mathematics in security of information is the border of mystery, and there's no rational explanation for it. And before we speak about the role of mathematics in cryptography, I'd like to briefly go over something, and I'm going to do this very quickly, about these history of cryptography, because it's not something that started being applied a few years ago, but rather this started several centuries before Christ, even though we must say that at the very beginning it was more of an art, more so than science. And in the Spanish language dictionary, when we look for the definition of cryptography, it says the art of writing with a private password or with an enigmatic and mysterious way. Where are the first examples of cryptography? I'm sure you've all heard about its use in Sparta and Persia. In several ceremonies, what they did was to write on a parchment, and when the parchment was rolled up, it was called a cytala. So cytala, when unrolling it, you could see the letters, and when the message reached its recipient, the recipient had to have the same sort of a stick in order to roll up the parchment and recover the message and retrieve the message. Another sort of encryption we all know of is the famous Caesar's encryption or encrypting, where he substitutes a letter with a letter that two letters ahead in the alphabet. And in these replacements, we have the Alberti encryption, and a special disk was designed for this disk that I'm sure kids have been able to see in cryptography workshops this morning. So therefore, in cryptography, this wish for security has been present.
And all of them have something in common. They belong to what we call today private key cryptography. So people that want to communicate, they agree on a key to encrypt the messages and communicate. They use different techniques, even though this might seem to be rather based on ingenious, but there's always a mathematical operation behind. But as we see, they do not use deep or serious maths. In private key encrypting that we use today, they use a different type of mathematics, but not at the level we wish to reach. At present, they use a flow encrypting or block encrypting, and behind all of them there are mathematical operations. But in fact, what was a milestone and change cryptography was the coming of public key cryptography. This is as recent as in 1976. As I said, cryptography was always on private key, and the use was for diplomatic or military purposes. Military secrets or state secrets were protected. As I said, the essential idea was that the same key had to be shared. In order to do so, both persons had to meet, or they should both access the key. The fact of getting the key that had to be communicated was always a tricky point. The fact of intercepting it might have fatal conditions, as in Maria Estuardo's case, she could be beheaded.
And when we see the public cryptography, this is the problem that we try to avoid, to have the key exchange and no longer be a problem, and for it to be able to send through a public channel. This pioneer work with this new idea has launched a new idea that breaks away with the previous one, because right now the encryption and decryption keys are the same. Well, and but there's the same level of difficulty. So what they propose in their work is that each user will have two different passwords or keys, one for encrypting and the other one for disencrypt. But the password or key they use to encrypt must be a key or password that only he or she knows, so that anybody who can see the messages that are encrypted will not be able to read them or see them. So this, in principle, is shocking. How can one do something in such a way that everybody can know how to encrypt and not know how to encrypt it, so decipher it? So there are what we call one-way functions. A function where a given element we can estimate or calculate the image of an element. But on the other hand, or the other way around, if I know an element which I know is the image because of the function, another, I have to find great difficulties in order to be able to estimate the element it is an image of. So when we see this work, they thought about using what could be more appropriate.
Para ver la primera que se utilizó, que ya aparece en el propio trabajo de Diffie-Hellman como una propuesta de hacer un intercambio de clave, el problema que se utiliza.
Well, here we use a problem that mathematicians call a discrete logarithm problem, because I don't know whether logarithms are still being taught. But it's the same idea than with logarithms, but in a discrete environment. And so here we have a cyclic group, an operation, and here with one element we can generate everything. We have an element generated by the group, and the rest of the elements that are obtained by multiplying G by itself.
Vuelve a ser
And
diferencia del G porque estamos en contextos de grupos finitos cuando planteamos este problema. Entonces, se elige un grupo finito.
so here we choose a finite group, and and here A selects randomly an exponent A, and they don't tell anybody who it is, but they calculate the power, and D receives this power and selects randomly B exponent, calculates the power and sends it to A, so that A, once has received the B power, obtains an element that B can also obtain by doing the operation in the inverse or reverse manner, because powers work as with the numbers. G. So what's the key? We need this problem to be complex enough so that if somebody is watching the network, what does he see? He sees these GA element. We have a problem of the discrete logarithm. If it knows G, it should be able to determine A. This is a problem of the discrete logarithm. There's a multiplication number of a finite element. In mathematics, we use the two-element body, but we have finite bodies with any element that's the power of a prime number. And bodies we no longer have an operation. We have two, the addition and the product. We can add, we can multiply, and we remove the zero that spoils the product, because any element multiplied by zero will result in zero. So without a zero, this forms a cyclic element with the multiplication. And if we choose a very large prime, it's very difficult to solve the discrete logarithm in this group. So this was one of the major problems we find that were used. And after seeing this sometime later, Gamal proposed a system which is based on the discrete logarithm. 2 years later, after this proposal, there's something used, another problem, and now we're going to formulate it in the easiest possible way, the factorization of large numbers. So the authors of the famous SRSA decided to apply the scheme defined by Hellman using the factoring of very large numbers. So they use this scheme. And what does this consist of? Whoever will design the key will do it with a slight trick. A very large number is built, but as a product of two large primes. So this allows when we want to calculate the function of an n number, we have to count the numbers smaller than n, and that's our n prime. And the way to define it is very easy. But if we think of a number like 128 digits, thinking about counting all the numbers that are smaller would take centuries. It's impossible to do it, not even with computers. So this is something that is difficult to know if we don't have the factoring of the number. So when you have all this information, you choose an exponent apart from all the things that have been added in order to ensure security, but in order for the system to make sense, it's got to be relatively prime with this value we have there. Why do we need this? Because we know that if we have two full numbers and we calculate its maximum common divisor, this is related to the numbers to which it's a maximum common divisor through an identity. And what it says is that this can be expressed as a whole linear combination of these two numbers. So in this case, since we know that E is relatively prime with phi dm, we may find another D element that states that the product of E times D is 1 plus a multiple of phi dn. This means that this D value has to be maintained secret because it will prevent anybody else from decrypting it. So here we show the exponent we've selected. And as a private key, we have to maintain this D that meets this condition. We maintain secret D and the two prime. But if we know the two prime ones, we know the D. So now, encrypting and decrypting is easy. If we want to have a text and translate it into a number, the text is represented by a number smaller than the module, and we calculate the E power of this text, module n. So the person who's intercepting this and doesn't know D doesn't know how to retrieve the X starting from its E power. But for us it's easy because what we need to do is to elevate this to the other E exponent that we have a secret and we retrieve the original one.
Los alumnos de primero de matemáticas ya saben desde ese año. ¿De acuerdo? Por tanto, sorprendentemente,
so surprisingly, part of the mathematics and the theory of numbers, there were some mathematicians that said that the beauty of the numbers were based on its uselessness. This was basic in order to define the first scheme.
Bien, podrán plantearse, de hecho, yo me parece que es una pregunta muy natural.
And so, in case people never, is it so easy, difficult to factorize a big number because it sounds so very simple. We've all heard about the screening of prime numbers. I can start calculating to see if it's a divider or not, but the problem has to do with the size of the number with which I want to try out the dividers. So here I've included a reference to the Zerma numbers. These Zerma numbers are numbers that the exponents of exponents were very difficult to write, so we used mathematicians in the programs with which we write mathematical programs, even though they're compiled. Letter CDN is 2 to 2 and plus 1. The exponent of 2 is 2 elevated at 9, and this is a Zermatt number. So F0 would be 2 at 2, 0, 2 at 1 plus 1, 3. F1 would be 5.
Pasa a ser 17.
F2 becomes 17. F3, 257. F4, 64,537. So numbers keep growing. So Zermatt, and I'm sure this rings a bell. He is one of the best-known persons in mathematics, where this famous theorem that he thought that the numbers achieved like this were all prime. And he didn't give much proof of this because the first 5 were prime numbers he knew. So he said that all numbers would be prime numbers. So when we calculated F5, as you can see, this is a 10-digit number figure. So Euler, one of the most brilliant mathematicians in history, factorized it. And this 641 was one of the first prime dividers he could think of. And he said it was a factor of the number. But a long time elapsed until we could say what happened with the next Zermatt numbers. So F6, for instance, that appears here on the screen, is a figure with 1, 2, 3, 4, 5, 6, 20 digits. And it was factorized as a product of 2 prime numbers, one with 6 digits and the other one with 14. But F7, for instance, that's got 39 digits, was factorized in 1970. So nothing yesterday if we compare this with Zermatt numbers when they were suggested by Zermatt. And this factorizing was done by using computers and a sophisticated algorithm in order to simplify factorizing. From then, always working with powerful computers, we could factorize F8, which is a figure that's got 78 digits and factorized as a product of 2 primes, one which is 16 digits and the other is 32, or F9, a number with 155 digits that keeps on, the number of digits keep multiplying, and it's factorized as the product of 2 primes. One of them is 49 and the other 91. So we conclude that indeed factorizing larger numbers is a problem that cannot be easily treated, but from a computational standpoint, it takes a long time. Not that we don't know how to do it, but it just takes too long to do it. And even with the help of a powerful computer that will simplify things if the figure is large enough.
Bueno, como ya comenté,
as I said earlier, the other original scheme that came up at the same time is the Gamal that uses a discrete logarithm. In the initial version of the we see that there's a group that's been developed that comes from the algebraic discipline, and this is a number that allows us to use smaller keys, so the encryption processes are much easier. So we see the Gamal scheme that's been developed with an elliptical curve through what is called elliptical cryptography. At the beginning, I said that cryptography is basic for security. Why? Well, why did I say this? Well, because just to illustrate how it underlies all security problems. And for instance, we may go into an HTTPS and we want to communicate with a server. Every time we do this, and I'm sure that this is something that is done millions of times a day, we use cryptography. Well, because the server and the user that are communicated do so because they share a key. And as soon as they get in touch, they start using the computer that the user is using, and they start using this algorithm. And so these two people that are communicating share a key, and they encrypt messages. So they sent them encrypted, even though they don't know, because this is something that the user's computer does with the server. But on the other hand, the server must be sure that he is actually communicating with a server, or not, and not with somebody who pretends to be the server. And this is something we can do with cryptographics and encrypting code that generates a label, for instance. And when the user receives that label, his computer checks that this corresponds to the key he or she has for authentication, and therefore this means that it must have been the server that sent it. So thus, we are sure that they can communicate in a reliable and secure way. And we can also use public password or key cryptography in this sort of communication. First of all, the user may download this public key from the server and then use this public password in order to encrypt his own, and from then on communicate through symmetric cryptography, because it is much faster. And in this case, in order to ensure and make sure that it is the server that's sending it, they use digital signature. So the server sends the message encrypted with this digital signature with some trusted identity. And this is really important in everything we do every day. For instance, every time we update a computer software, if our computer wasn't sure that this updating has been sent by the program's programmer, we could install a pirate programmer instead of an update that could destroy everything we have in it. So therefore, the type of processors, it's essential to have a cryptography, and obviously, looking for security, bear in mind that absolute security doesn't exist. That is, cryptography is constantly a race, trying to do safe schemes in order for others to look for vulnerabilities, and the perfect scheme doesn't exist. We're not going to be able to find one that will be able to withstand anything. So apart from these two problems that we've mentioned and that have been used in cryptography, there's another one, apart from the famous ISA and logarithm and elliptical curves. This gives rise to the cryptography of elliptical curves that is used in ID cards, where you see the identity of the person, and he or she can even sign documents with it. So here I've selected 4 following some newer ideas, and I wanted to tell you that this is slightly different from what I've been telling you of so far. We have the hash cryptographic functions. A hash function or a summary function is a function that associates arbitrary longitude with a fixed m length. But in order for a hash function to be used for cryptography, there are certain requirements. We cannot use just any hash function. So there's requirements about efficiency. There's got to be efficient implementations that will allow us to estimate the image of an arbitrary length image, and on the other hand, there's going to be other safety security conditions must be met. One is called a resistance to collisions, resistance to the second other image, or resistance to a target collision. And they are very close, but we can try and define them superficially. Resistance to collisions means that it will not be impossible to find two elements that will have the same image according to the hash function. If we know the summary of a sequence, it is for us not to be able to estimate the sequence it is a summary of. What must be difficult for us is the following. If we are given an element which I know is the hash of somebody, of one, and whose hash it is, and to be able to find another element that will have the same summary function.
And resistance to objective collision. If we select a specific target, it wouldn't be difficult to find another element with the same image based on the hash function that we specified. It must be said that currently there are no families of hash functions that are at the same time efficient and secure. And this security can be duly demonstrated with what mathematicians consider a true demonstration of security, that it can be demonstrated or proved with a series of steps and using specific tools. What happens? Problem is that some work, and it seems that they work because they're able to resist the attacks that they are constantly receiving from cryptographers. So we understand that they are reasonably secure. I mean, this security cannot be demonstrated, but they are reasonably secure. For a long time, SHA-1 was used, but then collisions were identified. And this endangers security, but the fact that one has been identified doesn't disable the function as such, but calls for, of course, examination. Whenever there's a hash function that is compromised, and this is something that happened with SHA-1, a collision was detected, and there are procedures that sometimes oblige us to lose some efficacy because they complicate the process, but contribute to the resilience or resistance. So there are hash functions that are apparently safe and secure and that can be used for cryptographic purposes. In order to use these functions, the only security parameter we have is the length of the summary that we associate to a random arbitrary chain. In this example, if we think about an attack that can be perpetrated to whatever hash functions using the birthday paradox, and I don't know if you're aware of the birthday paradox, it's simply if we ask ourselves, how many people are there in a room, or should there be in a room for the likeliness of two of them having the same birthday being at least 0.5? Well, the answer is much lower than what might expect. 23 people. Whenever there's 23 people, the probability of having the same birthday is 1/2. If there are 90 people in a room, 50 people in a room, you're going to exceed 90% of likeliness. And this is surprising in itself. That's why it's a paradox. And using this fact, an attack was designed that works with all hash functions. If we want a hash function that has an n length, and an attack is designed based on the birthday paradox, the time required to find by brute force a collision is 2 to the power of n halves. So currently, for us to feel safe, we would need a length of at least 256 for the time required to find the collision would be long enough, and therefore not a matter of concern. It seems that with a quantum computer that is sufficiently powerful with enough quantum doors, time is not reduced as much. It would be 2 to the power of n thirds, so it would be enough to broaden the length of the hash function to 384. If we don't want resistance to collisions, but second image, the birthday paradox wouldn't help us design an attack. We need to do this using brute force, and the time would be 2 to the power of n, and the length would be smaller. We wouldn't need such a long length. And it seems that in this case, quantum computers don't have a devastating effect, and would simply reduce to 2 to the power of n half, so the length wouldn't be multiplied significantly. Another type of problems that we need to consider when considering cryptography are those that are linked to reticles and more specifically short vectors. What are we really talking about? When we talk about reticulum, it's a subgroup of a vectorial space of dimension n. If we think about plane points, we think about the reticulum generated by 0, 1, and 0, 0. We would be drawing like fisherman's net or mesh, and the vortexes would be the point of the reticulum. So in a reticulum, we had k vectors that are linearly independent, and all linear combinations of those vectors give us a reticulum. So, in the reticulum, we can have more than one base, or we can generate this with different bases. And what do they share? Well, the fact that they have the same number of elements. If I generate a reticulum with a base of 4 elements, whatever other base I find will also have 4 elements. One of the problems that we know that is hard to solve in computational terms is finding in a random reticular a vector with the shortest length, length understood with Euclidean metrics that we've studied at school. And this is a problem that can be exploited with cryptographic purposes. Another problem related to this, although slightly different, is what happens when we get a point of the Rn vectorial space and find a vector from the reticulum that is as close as possible to this point. And this is a problem that is considered to be difficult to solve. Unless there is another significant problem, which is that of reduction of a reticulum base, i.e. finding a base with good properties. I'm referring to base made up of small size short length vectors. And this problem is also tough. Reduction can be fixed in different manners. We can demand more or less to the elements of the base, but it's an important problem because if we want to design an efficient procedure with traps that allow us in a reticulum to find a short length reticulum, it's not the same to work with one base or with another. With some bases, the problem is impossible to solve. There's no reasonable time to do this. But there are some bases with small or short vectors with which you can work, and the process can be done in a reasonable period of time. So, reasonable processes to calculate shorter vectors require as a routine the ability to calculate appropriate base reductions. Good. Let's move on. Another problem that uses what we call error corrective codes. The idea behind error corrective codes is as follows. Initially, one may think that this is close to cryptography and that what we do is also encrypt, but what we do truly is code, because the goal is essentially different. In cryptography, we modify a message and we encrypt it so that people don't know what we're saying. In corrective codes, what we try to do is ensure the reliability of information, i.e., if we transmit info through a noisy channel, and there is some sort of perturbation, sound, electromagnetic perturbation, or physical alterations of the message. When the message reaches the destination, we need to be able to detect that there have been alterations in order to correct them. So, for example, we use satellites that take pictures. So let's imagine that we send a satellite to take pictures of the moon in a specific phase to be then sent back to planet Earth. And we can say, well, there's no problem if when we receive the picture it's flawed, it can take further pictures, but maybe that's not possible because the position of the moon has changed and the new picture sent from the satellite will not provide us with the info we're looking for. That's why it's very important that we're able to correct the errors produced. And on a daily basis, computers are constantly managing corrective codes, error corrective codes, because the data that are stored need to be stored with a code that, if there's an error in the processing of that info, allows to detect that error and to recover it in an automatic way. Error corrective codes are another important field of research that resort to mathematics, and in this case, we're only going to think about linear codes, okay? Linear codes are always built based on a vectorial space on a finite body. As you know, finite bodies are in this field superstars. In the past, because of the influence of physicists, we only talked about real numbers and complex numbers in the best of cases, and we left aside rational numbers and finite bodies. But with these new theories, the theory of finite bodies has played an essential role. It's no longer something sophisticated, something very sophisticated that we algebra experts invented and now play a stellar role. So we're talking about finite bodies, a series of elements in a finite body, and that hold or use up a space of dimension k. The code, what it does is code elements that add additional elements up until n, so that those elements that don't contain info allow us to detect errors and then correct them. So these parameters are essential together with other elements that provide us with corrective capabilities. When we want to build a code, we do this by multiplying matrices. We have a generating matrix k times n size, and we get the catchable that contains the digits of the message, and obtain the number we're looking for. In this vectorial space and a finite body, we also have a metric that is very different to Euclidean metrics, and this is what we call Hamming distance. And what Hamming distance says is that tells us how many positions are different between two different elements. That's what this Hamming distance tells us. The problem when it comes to decoding is that we're trying to find effective mechanisms so that when we receive the coded word, we're able to detect errors. If it's not the case, we recover the info received immediately. But if there have been errors, we recover the correct info, the word that was truly sent before the channel altered the word through noise or because of whatever reason. And of course, we cannot correct as many errors as you wish. The number of errors we can correct is determined not only by the physical features of the channel, but also by the corrective capability of the code we are using. And this corrective capacity can be known a priori by knowing the minimum distance of the code, i.e., by knowing the smallest distance between two code words. When we build these codes, the words of the code need to be sufficiently separated so that the minimum distance between them is sufficiently big to allow us to correct errors. In order to correct an error, you need a minimum distance of 3. because if we have a minimum distance d, the code can detect -1 errors and can correct d divided by 2 errors. When we design these codes, what we're looking for is for the dimension to be big enough. Dimension is k. It's the subspace because this basically tells us that we can code many words at a time. The length can be too big, however, because the length adds or aggregates control digits in order to correct errors. If we aggregate a great deal, we will be losing efficiency in terms of money and time because the time devoted, of course, costs money. And on the other one, we want distance to be sufficiently big to be able to correct a reasonable number of errors. And of course, these three objectives are sometimes incompatible. They are interrelated, but we can contribute to one but be detrimental to another. Good. We know that the decoding problem in linear codes is an NP-complete problem, i.e., a problem for which there is no known algorithm that can solve it, and should it exist, it would probably tell us that class P and class NP coincide. Therefore, this could only be solved in polynomial time with an algorithm. However, it is also known that there are some codes, the so-called GOPA codes, for which if we use a matrix, a specific metric for these codes, we can do this in a reasonable amount of time. And how can we build them? The GOPA codes from a mathematical point of view are very simple. We use irreducible polynomials with a finite body. And the fourth mathematic problem I wanted to talk to you about is the MQ problem, multilinear quadratic problem, that tells us that if we have polynomial equations in several quadratic degree 2 variables with coefficients in a finite body, finding common solutions to all these equations is a very tough problem. In fact, if the number of variables that we are using and the number of polynomials are comparable and have a comparable size, this problem is NP-complete as well. Why have I chosen these problems? Well, because based on these problems, there are some cryptographic constructions of encryption systems and digital signature systems that do shed hope and light to the continuity of cryptography in a post-quantum period. We know that currently the two systems that are most used in cryptography are RSA and elliptical curve cryptography, or EC. And this is, of course, a personal opinion, and one of the reasons why they are used, aside from their effectiveness, and they're also efficient and they can be done in a short period of time, and it's because during the past years, many implementations have been done. There is an industry around this, and they have improved the problem, know how to choose module N in the RSA or what curve needs to be chosen, and some implementations are secure because they've been honed and fine-tuned each time there was an attack against them. The concept of quantum computer that was introduced in the 80s unveiled an underlying threat to public key cryptography, because it seemed that quantum computers, should they be built, would allow for very complex equations and transactions to be done in a very short period of time. The threat grew when in 1994, Peter Shor presented quantum algorithms that allowed to factor whole numbers and calculate discrete algorithms in polynomial time, meaning that using RSA for elliptical curve cryptography, and having a quantum computer that was sufficiently powerful to do a sufficient number of quantum operations, it would take just as much time in encrypting RSA and elliptical curve. So both of these procedures would no longer be useful. And of course, we need alternatives, B plan in our portfolio. So in case quantum computers are built with enough capacities, we'll need alternatives, because small ones with 6 or 8 quantum doors, so of course those have been built, but that's not enough. And until those large quantum computers are built, we will be able to continue using cryptography. Well, I'm going to run over this because it's a bit late. But aside from the Sherwood algorithm, we have the Grover algorithm, which is a quantum algorithm that allows you to conduct a search of data in an orderly database. If we're given a handbook or a telephone book that is not ordered, it would be impossible to find a telephone number. And this algorithm allows you to find in an unordered database in time that is the square root of n. And if a quantum computer is developed, this would also be a factor. For example, the AES, could be affected, but the effect is not as devastating or dramatic as in the Shor algorithm. It wouldn't destroy the use of AES, the Advanced Encryption Standard, but we would have to increase the number of keys. There are some digital signature schemes that are being used that seem to be secure and efficient, and that are based on hash functions, as mentioned earlier. There are no encryption systems based on these functions as of today. There is much research to be done because there are some drawbacks. The design is based on binary trees and single-use keys, and you need to keep a log of the keys used. The storage, therefore, capabilities need to be high. But there's room for hope here. It's promising, and it seems that we will be able to have digital signature schemes based on hash functions that can be used securely and efficiently. There's also multivariable cryptography based on the problem that I previously described. There's a public key scheme, and what this does, as you can see on screen, as other schemes based on corrective codes or on Reticula, is basically put a trap on a good function that works well and mask it with others, so that once masked, the image that you can see is of a ransom image that cannot be decrypted. And that's what we do here using multivariable cryptography. For the sake of time, I'll move on. I'll skip some slides. I'd just like to say that we can also build encryption schemes with multivariable cryptography. We have digital signature and we have encryption. And for encryption purposes, we demand more from that good function. Aside from be able to find pre-images, we're able to re-inject. And there's also code-based cryptography. And the scheme that's still in force for code-based cryptography was introduced by Michaelis in 1978, the same year as RSA. This system is considered to be secure and safe because since it was introduced, it suffered ongoing attacks to expose vulnerabilities and weaknesses. There was this huge RSA attack that was launched by the inventors of RSA, but it has survived up until now. It's true that at the beginning was less efficient than RSA, but it's been improved And there are some code-based schemes that are efficient. What it does, as in the previous case, is mask the good generating matrix that allows us to decode a code with two other matrices, a permutation and a symbol matrix, so that the owner of the key can decipher, but those that try to do so using brute force will have problems in decoding a linear code, and this is an NP-complete problem which is hard to solve. In this case, aside from encryption, we have digital signature schemes, an encryption scheme based on this. And regarding Reticula, I like to say that there is some cryptography based on Reticula. This cryptography, what it does, is exactly the same as the previous ones. We have a Reticulum, and we have info that tells us that the base is good, that the length is short, and therefore we can implement in an effective manner a procedure in order to calculate the shortest vector. So what we do is use it for encryption purposes, and we mask. And what we provide is another base with poorer properties than that doesn't allow to calculate the shortest vector. How do we encrypt this? By introducing an error so that what we obtain is not a vector from the reticulum. We then recover the message because we know how to calculate the vector of the closest reticulum, but the person that wants to intercept it is unable to do so. In reticulum-based cryptography, what we're seeing is that great progress is being made. Much work has been done to fine-tune it, and digital signature schemes have been designed, but there are some security issues associated. Why? Well, because the implementations that have been done to make them efficient are not based on reticulum issues, but others that stem from them, and therefore we cannot demonstrate or prove security in such an efficient manner. There are important drawbacks and cons to this, and these have been used in homomorphic cryptography. Homomorphic cryptography is another subject that has drawn attention for a long time. Some people said that it was the holy cross of cryptography, and the goal was to design encryption systems to operate with encrypted data. And this may seem unnecessary, but if you think about examples, you can see the usefulness. The cloud stores data, and some hospitals store disaggregated data from patients that they then encrypt to send to the cloud. What's normal is to send the data encrypted to protect the privacy, but those data can also help us calculate statistical data and help us take diagnosis decisions. The statistic decisions that are made are simple, sometimes averages or standard deviations. And if we have homomorphic cryptography that allows us to operate with encrypted data, so that the encryption of the sum is the sum of the encryptions, when we want to do statistical calculations, we don't need to download data, decipher them, do our math, and then upload them again after encrypting them again. No, we decipher, we do the math, and we save a lot of time in the process. The solution to homomorphic cryptography, the first design of homomorphic cryptography appeared in Morphy's dissertation. It was reticulum based. So as a conclusion, I would say that there is a huge field of work to conduct research, to see how we can apply maths to promote cybersecurity and cryptographic systems, both in terms of digital signature, and encryption can be used. The idea is that cryptography can have a promising future in a post-quantum scenario. These are the references that I've directly quoted. I haven't included them all, but if you're interested, I can give you the indirect references. And thank you very much, everybody, for your attention.